Hi there! In this section, we are going to explore two fundamental approaches in machine learning: supervised and unsupervised learning. Think of supervised learning like learning with a teacher who shows you the correct answers. For instance, imagine you're learning to identify handwritten numbers. In supervised learning, you'd be shown thousands of images of numbers, and each image would come with a label saying, "This is a 7" or "This is a 3". The system learns by seeing these examples and their correct answers, gradually understanding what makes a 7 look like a 7. On the other hand, unsupervised learning is more like exploring and discovering patterns on your own. Instead of being told what's what, the system looks at the data and tries to find meaningful connections and groupings. A great example is when you have a bunch of news articles from different websites. Without being told what categories exist, an unsupervised learning system can group similar articles together, putting sports stories in one cluster and political news in another. The key difference is that supervised learning requires labeled data, so it needs examples where we know the correct answer, while unsupervised learning can work with raw, unlabeled data and find patterns independently. And both approaches have the unique strengths and are used for different types of problems in artificial intelligence. Here are the different techniques listed from the supervised and unsupervised learning. So in supervised learning, we have, for example, the logistic regression, linear regression, decision tree, and neural networks. And on the unsupervised one, we have, for example, clustering, association rule learning, probability, density, and dimensionality reduction. And we will have a look at each of them in detail. Let's start with logistic regression, one of the fundamental supervised learning techniques. Think of it as a decision maker that helps us answer yes-no questions based on input data. And what makes logistic regression special is its ability to take various inputs and predict which category something belongs to. For instance, imagine predicting whether a student will pass or fail a course based on the number of logins to the courseware. This is a binary classification problem, so just two possible outcomes. But logistic regression isn't limited to just categories. In multiple class classification, it can handle several categories, like classifying animals into cats, dogs, or rabbits. And the key is that we need labeled training data to teach the model what the correct classification should be. Then we have linear regression. So unlike logistic regression that gives us categories, linear regression predicts actual numerical values on a continuous scale. Think about predicting house prices. You might consider factors like the house size, its age, number of rooms, and location. Linear regression helps us understand how each of these factors contributes to the final price. It draws a line through our data points that best represents the relationship between these features and the price. And what's fascinating about linear regression is its widespread use in real-world applications, from predicting sales figures to estimating student performance based on study hours. And the key is we need to have historical data with known outcomes to train the model. Decision trees are perhaps the most intuitive of all machine learning techniques. Imagine playing a game of 20 questions, and that's essentially how a decision tree works. It breaks down complex decisions into a series of simpler binary choices. Let's take an example of predicting customer churn. The decision tree might start by asking, has the customer logged in within the last 30 days? If no, it might predict high churn risk. If yes, it might then ask about their average decision time, and so on. Each branch in a tree represents a decision point, leading to a different outcome. And what makes decision trees particularly valuable is their transparency. You can literally see how the model makes its decision by following the path from the root to the leaf. And this makes them excellent for situations where we need to explain our model's reasoning. Neural networks represent the more complex end of supervised learning techniques. Inspired by how our brains work, they consist of layers of interconnected nodes that process information in stages. So think of each node as a tiny decision maker, taking in information, processing it, and passing along its conclusion to the next layer. What makes neural networks powerful is their ability to learn incredibly complex patterns that might be impossible to program explicitly. A classic example is handwriting recognition. When you write a number, the neural network processes the image through multiple layers, each looking for different features, from simple lines and curves in early layers to more complex patterns in deeper layers. And this layered approach allows neural networks to tackle problems that would be extremely difficult for simpler algorithms. Okay, now let's have a look on the first technique in unsupervised learning, clustering. Clustering is perhaps the most intuitive type of unsupervised learning. Imagine you have a pile of mixed fruits and you naturally sort them into groups. All the apples together, all the oranges together, and so on. And that's exactly what clustering does with data. In real world, companies use clustering to group customers with similar shopping patterns or to identify different types of network traffic for security purposes. The AI finds these groups without being told in advance what the groups should be. Then we have the probability density. Probability density is like teaching AI to develop a sense of what's normal and what's not. Think of a temperature sensor in a server room. It learns the typical range of temperatures throughout the day. When it sees a temperature that's unusually high or low, it can flag this as a potentially problematic. And this technique is particularly useful in monitoring systems and detecting anomalies that might indicate problems before they become serious. Our final technique, dimensionality reduction, is about simplifying complex data while keeping the important parts. Imagine taking a detailed photograph and reducing it to just the essential elements. That's what dimensionality reduction does with data. It's particularly useful when we have data with many features or dimensions and we need to focus on what's most important. This technique helps make other AI processes more efficient and can help remove unnecessary noise from our data. So let's examine when to use supervised versus unsupervised learning in your AI applications. The key difference lies in your data and objectives. Supervised learning, as we already know, is your go-to approach when you have labeled data available. This means you have examples where you know the correct outcome. For instance, in email spam detection, you have emails already marked as spam or not spam. Similarly, in image recognition, you have image labeled with what they contain, and in stock predictions, you have historical data with known outcomes. Unsupervised learning, on the other hand, works with unlabeled data, where you are trying to discover patterns or structures within the data itself. This is particularly useful in scenarios like customer segmentation, where you want to group customers based on their purchasing behaviors without predefined categories. It's also commonly used in recommendation systems and when organizing large datasets where you want to find natural groupings. The choice between these two approaches ultimately depends on whether you have the labeled data and what you're trying to achieve. If you know the outcome in the labeled data, go with supervised learning. If you're exploring patterns in unlabeled data, unsupervised learning is your friend. So you might ask if there is something in the middle, and the answer is yes, and this is called semi-supervised learning. So this is a combination of supervised and unsupervised learning techniques. And this is particularly useful when you have a small amount of labeled data alongside a larger volume of unlabeled data. And by using both types of data together, we can achieve better accuracy and efficiency than we would by using the labeled data by itself. Let's have a look how this works. So the process of semi-supervised learning follows a specific sequence. The system first works with unlabeled data to identify patterns and structures within the information. Then it uses the smaller set of labeled data to refine its understanding and make specific classifications. And this approach is particularly cost-effective because it reduces the need for extensive data labeling while maintaining a high accuracy. So you might ask if there is something in the middle, and the answer is yes, and this is called semi-supervised learning. So this is a combination of supervised and unsupervised learning techniques. And this is particularly useful when you have a small amount of labeled data alongside a larger volume of unlabeled data. And by using both types of data together, we can achieve better accuracy and efficiency than we would by using the labeled data by itself. Let's have a look how this works. So the process of semi-supervised learning follows a specific sequence. The system first works with unlabeled data to identify patterns and structures within the information. Then it uses the smaller set of labeled data to refine its understanding and make specific classifications. And this approach is particularly cost-effective because it reduces the need for extensive data labeling while maintaining a high accuracy. And now finally, let's have a look where this is getting used in the real world. So for example, in fraud detection, the models can learn from vast amount of transaction data and then refine their understanding using confirmed fraud cases. For sentiment analysis, organizations can process large volumes of customer interactions and enhance accuracy with labeled examples. And finally, document classification systems can handle extensive collection while improving precision through categorized samples. In our next section, we will explore another fascinating type of machine learning, the reinforcement learning, which takes a completely different approach based on rewards and action. Thank you for watching, and I see you there.